How do photonic integrated circuits work in photonic qubits? Imagine a tiny chip that can control particles of light to perform complex calculations. That's what photonic integrated circuits do in the world of quantum computing. They bring together many optical parts on one small piece of material, making quantum operations more practical and scalable. Instead of electrons, these circuits use photons, particles of light, to carry quantum information. This approach offers advantages like faster processing speeds and less interference from environmental noise. A photonic integrated circuit is made up of tiny pathways called waveguides. These waveguides are like optical highways that guide photons through the chip. They use a principle called total internal reflection, which keeps the light confined within the waveguide, similar to how a fiber optic cable works. These waveguides connect different components such as sources that generate single photons, devices that change the phase of light, splitters that divide photon paths, and detectors that measure the photons at the end. In photonic quantum computing, qubits are often encoded using a method called the dual-rail scheme. This means a qubit is represented by two separate waveguides. If a photon is in the first waveguide, it might representing the zero state. If it's in the second, it represents the one state. When a photon is in both waveguides at the same time, it creates a superposition, which is essential for quantum calculations. This encoding makes it easier to manipulate and read the qubits using linear optical elements. Key parts of these circuits include single photon sources, which generate photons on demand. These sources often use nonlinear optical processes or tiny quantum emitters integrated into the chip. Phase shifters are used to adjust the phase of the photons traveling through the waveguides, which is vital for performing quantum gates. Thermo-optic phase shifters change the refractive index by heating, while electro-optic phase shifters do it faster using electric fields. Beam splitters and directional couplers are passive components that split or combine photon paths. They are essential for creating superpositions and entanglement, which are the building blocks of quantum algorithms. Detectors are integrated into the chip to measure the photons after processing. These detectors need to be highly efficient to preserve the delicate quantum states and avoid losing information. Because quantum states are fragile, minimizing photon loss is very important. Photonic integrated circuits are designed with low-loss waveguides and high-efficiency components to keep the quantum information intact. Using silicon photonics, which is compatible with existing semiconductor manufacturing, makes it easier to produce these chips at scale and integrate them with classical electronic control systems. These circuits enable the construction of scalable quantum processors that can perform any linear transformation on photonic qubits. They also support measurement-based quantum computing, where the process relies on measurements to drive the computation forward. Beyond computing, photonic integrated circuits are key for secure quantum communication systems like quantum key distribution and quantum teleportation, where they help transmit quantum information safely over long distances. In essence, photonic integrated circuits work in photonic qubits by bringing together photon generation, manipulation, and detection on a single chip. They use waveguides and optical components to encode, process, and measure quantum information carried by light. This technology is paving the way for more practical, stable, and scalable quantum computers and communication networks.